So welcome back. So continuing on from where we left off, which is probably not good news because you've probably forgotten. So what we saw is that, well, the quantum walks, discrete quantum walks that people use most often, are what we would call two reflection walks, so that the transition matrix U is a product of two reflections. Okay. Now there are other types of walks we will look at, but commonly that's the most common one. Now there's a special case called an arc reversal walk, which I'll say more about as we go on, and I defined in the last lecture, and that's a special case of the two reflection walk, and so that will be the main example. Now to get the two reflections, the trick is that we can get reflections from partitions of an underlying set. And so in the last lecture, I was describing how I get those. I get the partitions, I get two projections. And then if P is a projection, then 2P minus I is reflection. And so projections give us reflections and vice versa. It's just that sometimes I'm not sure whether it makes a difference which you work with, but we choose to work with the projections as a rule. So the problem is ideally we'd like to find a spectral decomposition for our unitary matrix U. Now it's normal, so it has one. Okay, but well, we don't really have, it's very difficult to work out what the entries of U are, and so trying to get the spectral decomposition of U directly, it's not at all clear how you would proceed. So we would like to work with the algebra generated by the two projections. So we have two projections, P and Q. And so we take the all linear combinations of products of P's and Q's. And so that gives us a matrix algebra, which is also the matrix algebra generated by the two reflections. And so in our case, that would only be R, reflecting an arc, and C, the coin matrix. So the algebra generated by R and C is also the algebra generated by the two projections. We'll be working two projections. Now, our life would be easiest if we could diagonalize simultaneously everything. The trouble is that P and Q in general, they're not commuting. Okay, so it's not at all clear how you would diagonalize it. Okay, and in general, if you a bit careless and try and be slightly more general, then I have nothing to say. But the case that we're dealing with, we have a bit of information. We have our two projections, so and the corresponding two reflections. Now the algebraic idea underlying this is that two reflections, so two elements of order two elements of order 2 generate the dihedral group. And we understand the representation theory of the dihedral group. And so we know, and that tells us we can break things up not into one-dimensional subspaces, which would be eigenspaces, but into one and two-dimensional subspaces. So what we're trying to do is to find a decomposition of our matrices. So we're going to write them in block diagonal form. We want each block to have size 1 or 2. If we could arrange for each block to have size 1, then we would have simultaneously diagonalized all the matrices and we would have a basis of eigenvectors, but that's not going to happen. Anyway, so we have to, well, here's the summary. So we've got two projections on n-dimensional complex space, and we want spectral information on this guy, which generates our discrete quantum walk, our two reflection quantum walk. And so we're going to work in the algebra generated by, or P and Q, which is equal to the algebra generated by R and C, because R is 2P minus I and C is 2Q minus I. And I'll call it a lemma, but if P and Q are projections on C, then C to the M is a direct sum of one-dimensional subspaces and two-dimensional subspaces. And so that means we can find a change of basis. So every matrix in A is block diagonal, and the blocks will have size 1 and 2. Now, we can find eigenvalues of 2 by 2 matrices. That at least is easy. Okay, so that we'll be able to use that to get the eigenvalues and eigenvectors and multiplicities of the of U in particular. Okay, but more generally of any matrix in this algebra. Okay, the physicists call this what we're doing. They appeal to something called Jordan's theorem. Now Jordan has a number of theorems. It's not quite clear which one they're referring to, but anyway, this is what we're going to prove. Okay, and so so ideally we would like to diagonalize everything. We can't do that, but we can in this case get dimensions 1 and 2. So let's start looking at the proof. Now, the first thing is that a one-dimensional A invariant subspace is spanned, well, a one-dimensional invariant subspace is spanned by an eigenvector. In this case, it would be a common eigenvector for P and Q. And there could be plenty of those, okay? Okay, so no problem with that, okay? So we're going to take all those common eigenvectors, and we're going to take the space spanned by the common eigenvectors, okay? Now, if that space was equal to the C to the M, we could stop and go for a coffee, but it's not in general. So we're going to take the orthogonal complement to the span of the common eigenvectors. So these are all the things where we couldn't break things up into one-dimensional things. Okay. Now, since P and Q are emission, this orthogonal complement is A invariant, which is answering the Y there. But you may want to think about that a little bit. So it's leaving the complement. It's leaving the complement invariant. Okay, and so that means we can essentially restrict ourselves to W and work out what's going on there. Now, there's one more remark which will seem a bit strange at this point, but we just want to notice that this matrix is emission. Okay, and quasi semi-definite what it's worth. And so W is spanned by eigenvectors for Q, P, Q. Now, the idea is we want to get two-dimensional invariant subspaces. So we've got to pick our first vector and then construct a second vector to go with it. Okay, and so our first vector is going to be an eigenvector for QPQ or something related to it. Okay, so W splits in the sum or spanned by eigenvectors for this. Okay, it's not clear why that should help, but it does. And it turns out there are two cases. One case is when this matrix acts as a zero matrix on W, and the other where it doesn't. The second case doesn't really happen, but so we'll start with the case where QPQ is not zero. So then we have an eigenvector. And the point is that U in this case is not zero. And so now we get, now we observe that mu applied to QZ is equal to this, equal to this, equal to mu Z. And so we just see that QZ fixes Z. So if Z is an eigenvector for QPQ and U is not zero, then Z is 6 by Q. So it's an eigenvector for Q, for what that's worth. Now we also see that Q applied to PZ, well, Z is equal to QZ, so it's equal to this, and that's equal to UZ. So the conclusion is that this subspace, the span of Z and PZ, is A invariant. Q maps Z to itself and PZ to mu Z. Q maps Z to P maps Z to PZ and PZ to PZ. So it's invariant. So we have ourselves a subspace which is invariant under the full algebra generated by P and Q. So every linear combination of products of P and Q leaves this two-dimensional subspace invariant. Okay, and so therefore we can represent P and Q fix their subspace, so you can represent them by two matrices. And as I said, we can compute eigenvalues and eigenvectors 2 by 2 matrices without any great trouble. So if PQ is not zero, we've got ourselves a two-dimensional eigenspace or two-dimensional invariant subspace. Okay. Now the other case is where the QPQ is not zero, and if Q is equal to 0 on W, then the algebra generated by P and Q is equal to the algebra generated by P on W, okay, because Q is doing nothing. And so W has a basis of eigenvectors of P and Q, which looks a little silly, but it's true. Now, so okay, so that's not going to be true because W doesn't have is not a sum of eigenvectors of common eigenvectors of P and Q. So Q is not zero on W. So we're assuming that QPQ is zero on W, but we're finding that Q is not. Okay. And if it's not zero, then the eigenvalues of Q are 0 and 1. And so there's a vector Z in W such that QZ is equal to Z. Q is fixing W. And so W is spanned by eigenvectors for Q. And the eigenvectors for Q have eigenvalues 0 and 1 because Q is a projection. And then as before, as QPZ equals QPZ, this is equal to 0, you see that the span of Z and PZ is A and PQ invariant. So in either case, we get that the span of Z and PZ is PQ invariant. And so we have a two-dimensional invariant subspace, and therefore we can decompose W into two-dimensional subspaces, which means that we can write any matrix in the algebra of by Q as a block diagonal matrix where we have some ones corresponding to the common eigenvectors and then a bunch of 2 by 2 blocks. Okay, and these guys here, Z, are eigenvectors for QPQ. Okay, so we have a decomposition. So the next step is to get some information out of that. So we want to get the eigenvalues. Now, so use the unitary matrix, so its eigenvalues lie on the unit circle. And so the real eigenvalues of U can only be 1 or -1 for what that's worth. Now, I should make one other comment. U is a real matrix. And so therefore its eigenvalues come in complex conjugate pairs. And so you can think of the eigenvalues as lying on the unit circle, but they're symmetric top and bottom. So if e to the I theta is an eigenvalue of U, then so is e to the minus I theta. Okay, so yeah, so that plays a role, at least implicitly, in some things we're doing. So the point is, the eigenvalues of U, the complex eigenvalues of U come in conjugate pairs because U itself is real. Okay, so my other comment is, if you're trying to get notes on this, the cheapest source will be Harmony's thesis, and I'll put a link to that on the webpage. We always have a book, but anyway, the thesis has got everything in there, probably in slightly different notation, but that's a good exercise. So if we have a projection, we can always write it. So it's a projection onto some subspace. We choose a north normal basis for that subspace for the image. That gives us a matrix. Those form the columns of a matrix I'll call L, and then you discover that P is equal to L star. So L is the matrix, is a matrix whose columns are a north normal basis for the image of P. And so we can always write our projection in that form. You can do this more generally for positive semi-definite matrices, but I want these to be orthonormal. So in particular, L star L will be the identity, okay, and ditto for Q. Now, maybe I'll scribble something here. Notice before I was talking about QPQ, which is equal to now M star D M star. And so we're working with this. Now, one argument, we're worried about eigenvalues. Now, one thing we'll be using a number of times is the fact that if A and B are matrices such that AB and BA, those products are both defined, then AB and BA have the same non-zero eigenvalues with the same oblicities. So let's move this to here. We haven't changed the non-zero eigenvalues, but M star M is the identity. So instead of working with QPQ, we can work with this matrix. Now, this is a smaller matrix because M's not square. M is the size of M is the number of vertices, or the number of columns of M is the rank of Q. Okay, so this is a smaller matrix, and so it makes sense to work with a smaller matrix if you don't. And so it's got the same eigenvalues. The only ones you're missing are zero eigenvalues, so we're not going to worry about those. So we're going to work with this guy rather than QPQ. Okay, so that's the adjustment we're making. And then we're going to pick an eigenvector for this matrix, and we're going to pick a constructor vector Z, which is L times Y. Okay, so Z's in the column space of L, so it's in the image of Phi, is what that's worth. So just a little bit of summary here. So we've got what P is equal to this, Q is equal to this, we've got an eigenvector Y for M star at PM, and Z is equal to MY. And so, well, I've now writing out the claim I just made verbally. we've got the following matrices quasi-semi-definite, and they have the same non-zero eigenvalues, the same multiplicities. Now, I did say we'd be using this more than one. Okay, first, so I'm using the tilde to denote having the same non-zero eigenvalues, the same multiplicities. Okay, so these two guys certainly, okay, by what I just quoted, that PQ is equal to P squared Q. And so I can move the P across, and so you get PQP there, and PQ is equal to PQ squared, you get QPQ. And so we get all these matrices have the same non-zero eigenvalues, the same multiplicities. Okay, so there's really 6 matrices that matter, this, and these 4. Okay, so I said this was an important fact, and it's going to get quite a bit of use in what we're doing now. Okay. The other thing I need, yes, here. Got to be a little careful. What I want to claim is that the spectral radius of PQ is less than 1. Now, PQ has the same non-zero eigenvalues, same multiplicities as PQP, and this is quasi-semi-definite. So the eigenvalues of PQ are non-negative real numbers. Okay, and so the eigenvalues of PQ are non-negative real numbers. Now, that doesn't make this quasi-semi-definite because it's not emission, but it's trying very hard. So the eigenvalues are non-negative. And basically, I want to know that the eigen, and so the eigenvalues are between 0 and the largest eigenvalue. And the point of these comments is that the largest eigenvalue is at most 1. Now, there's a wrinkle hiding here. I would say the 2 norm of M is defined to be the supremum of x star mx over the unit vectors. Okay, now but look carefully, so that the 2 norm of the identity would just be the maximum of x transpose x over unit vector, so it will be 1. Now, if I use our Frobenius norm, trace of PQ, then the norm of the identity, then I comma I would be n. So this is not the Frobenius norm. Now, it's not going to matter because we're just going to use it now and it'll go away again. And it's a reasonably easy exercise to show, actually, this works for the Frobenius norm too, that the norm of the product is less than equal to the product of the norms. And so the third fact is if M is emission, then the norm is actually the spectral radius of M, which you can sort of see from this. And so it follows if P and Q projections, well, P's got norm less than equal to 1, Q's got norm less than equal to 1. So by this, PQ's got norm less than equal to 1. So that tells me the eigenvalues of PQ or PQP or QPQ all lie in the interval 0, 1. And we'll need that at some point. Although by the time I use it, you'll have may well see it, may not notice it. Okay, so I've got a proof there, but I'm not sure it's worth. Well, okay, let's do it. So if so, I'm going to prove this fact. So I'm using rho of M to be the spectral radius, and I'm using this for the this norm, and I'm using the fact, which I could probably make an exercise if I felt like it, that it's sub-multiplicative. The norm of M times N is less equal to norm of M times norm of N. Now, if P is a projection on a Hilbert space, where I've got an inner product, and this inner product is 0 because P and I minus P are orthogonal. And so when you expand this, you get, well, actually I don't quite know what I'm doing. So then the inner product of X with itself, squared norm of X, well, it's Px plus I minus Px, P plus, when you multiply it out, the diagonal terms become 0, and so you get the norm. This is Pythagoras theorem, the norm of x comma x is equal to Px comma Px plus I minus Px comma I minus Px. And so since this is non-negative, because I minus P is positively definite, this must be less than or equal to this, which is 1. If I choose x to have norm 1. So that gives me the proof of that. So one way or the other. Yeah, okay. Yeah, okay, so that's what I just said. Um, so basically what we're going to do is get some information about the eigenvector. So our assumption is we've got an eigenvector y of MPM and a vector z, which is m times y. Okay. Now m is number of columns is the rank of q, so it's so z is longer than y. And so I'm going to break it up in a number of claims. So the first thing is if so I know that the eigenvalue is this guy lie between 0 and 1. Okay, so so the if y mp m star p m y is equal to y, the claim is that z lies in the image of p and the image of q, and so that means that p of z is equal to z and q of z is equal to z. Okay, now okay, so here's the proof that if this is true, then I just take I replace p by I minus p and expand. And on the other hand, we know that this is not negative because I minus p is positive semi-definite. And if U matrix, if U star matrix U is equal to 0, positive matrix, then MU is equal to 0. And so if this is 0, then this is 0. And so then it follows that MY is in the image of P because it's in the kernel of I minus P. Okay, and what I'm saying here, since QMY. And so this is just showing us that MY is in the image of Q. Okay, so that's that. Okay, so if we have an eigenvector, okay, so it's clear. Now the second one is when there's 0. Okay, so M star PMY is 0. So we've got this smaller matrix. It's positive semi-definite. The eigenvalues are between 0 and 1. And so we're now looking at case where 0. And that claim now is that MY is in the kernel of P and the image of Q. Okay. And so as before, we have 0 equal to, because this is 0, we get this is 0. And because P is positive semi-definite, we get this. So MY is in kernel of P. As before, QMY is equal to MY. Oh yeah, because Q is equal to same argument, QMY. Yeah, okay. So Q is M star M, and so these cancel because M star M is the identity. So Q and Y is equal to Y, same as before. Okay, and so we get that the MY is in the image of Q. Now it's just as a remark here, note that in the first case you'll find that U is 2P minus I times 2Q minus I. And you get that UZ is equal to Z, and in the case 2, you get UZ is equal to minus Z. Okay, so we're taking care of the real eigenvalues of U. And so this is the point where I need the, why I had to fuss about the largest eigenvalue of PQ. So let's assume now that we've got an eigenvector for MPM, M star PM with eigenvalue U, which between 0 and 1. Okay, we've done the 0, 1 case. Okay, and we define theta by satisfying the equation cos theta equals 2 mu minus 1. We'll come back to that. Then the claim is that this vector is an eigenvector for U with eigenvalue e to the I theta, and this vector is an eigenvector for U with eigenvalue e to the minus I theta. Okay, so basically what we're doing is we're getting the eigenvalues of U from the eigenvalues of this guy. Now, U is number of arcs by number of arcs, where this is just number of vertices by number of vertices. So this is a smaller matrix. Okay, and more than that, we're actually getting the eigenvectors. Okay. So this is where we have to do a little bit of work. So we're going to assume that we've got an eigenvector y for m star PM, this eigenvector value u, and then qz, y is my, q is m star equals the same y. So qz equals z, and qpz equals mu z. And so therefore, the z and pz span a subspace which is invariant under p and q. So, okay, at this point, what do you do in the algebra? If you've got a matrix fixing a subspace, you start writing down, or you've got a linear mapping fixing a subspace, you start writing down the matrix that represents the linear mapping. Okay, so the linear mapping I care about is U, and I claim, so I can, given I know what P and Q do, I know what P minus 2P minus I and 2Q minus I do, and so I know what U does. And so after a bit of calculation, you get that if you apply to this matrix, which is long and skinny, so it's 2 columns and a number of arcs for rows. And so this matrix, well, U's leaving the subspace invariant. So this product must be equal to the original matrix with a 2 by 2 matrix applied on the right. So this is, on the right-hand side, we've got a matrix with 2 columns, each of which is a linear combination of Z and PZ. Now, this is just your standard linear algebra. That, as I said, you're finding a basis for an operator on a subspace. It might get slightly confusing because you want to think of this as a matrix, but this is a number of arcs by number of arcs matrix, and this is going to be this is a 2 by 2 matrix. But the point then is that so the eigenvalues of C are eigenvalues of U, and there are 2 of them. Okay, and so now the other point to notice took me a while. The determinant of this matrix is 1 for what it's worth, so we know the product of the eigenvalues is 1, and the sum of the eigenvalues is 4 mu minus 2. So you can write down the quadratic equation. Let's actually do it just for the fun of it. So you get the equation t squared minus 2 t plus 1 would be the characteristic polynomial of C. Now, and so the trick is if we put make this assumption, then you discover that the eigenvalues of this matrix are e to plus or minus I theta. And with some more work, you see that the eigenvectors of the span are as given. Okay, so I'm not going to go through the dirty details, but it's more a matter of keeping the notation straight. So now we have all the eigenvalues and all the eigenvectors for the transition matrix. Okay, and so then, well, there's a few more details. We want to work out some multiplicities, but particularly the multiplicity of 1 and minus 1. But once we've done that, we can write down the spectral decomposition of U if we need it. Often we just need the eigenvalues, so we'll leave it at that. And I've written as a corollary here that the eigenvalues of U are determined by the eigenvalues of M star PM. Okay, so now this is well and good. In the real world, it's not quite enough because we may not have nice, this is well and good. We only need to work out what's going on in this smaller matrix. And so for numerical work, this might be great. It's hard to actually see anything and to relate properties of this to the system from the situation where you derived your projections. So we'll need to go further. But this is in some sense, the big step. We've reduced the computation of the eigenvalues and the eigenvectors to information about this matrix. And we'll see that in many interesting cases, we can get that information about that matrix very easily. Now, I may have to come back to that. It's possible to compute the eigenvalue multiplicities I haven't done it here. It's in harmoniesthesis. But I've shown you that we can get the eigenvalues. And the reason we can get the eigenvalues is because we've got this two-dimensional invariant subspace for U, and we know how U acts on it. So therefore we get this matrix representing U. So its eigenvalues are eigenvalues of U. Maybe I'll draw a little picture here. In a sense, what's happening is, okay, imagine this, it's a unit circle. You might need a good imagination. And what's happening is that the eigenvalues of U, as I said, are symmetrically placed about the real axis. And so the eigenvalues of MPM are lying on the real line. Apologies, semi-definite. Now, the point I want to make here is if you've got a unitary matrix, and I know the real value, and I know the real value of an eigenvalue. Okay, so I know this point on the line. Then I know there's only two choices for the eigenvalue of U. So if you give me the real part of an eigenvalue of unitary matrix, I have only two choices. I know, I only have two choices for the eigenvalue of U. And if I know that U is real and both of them are there, then I've got no problems. Okay, and so the eigenvalues of MPM can align this interval -1 to 1, and that's what gives us and then they give us the real parts of the eigenvalues of U. So, any questions at this point? Okay, so I said we can get the spectral information from M star PM. I've shown you how to get the eigenvalues at least. There's other questions that we can get. So to go further, I need to think about the actual application. Now in our applications, P and Q are coming from, our projections are coming from partitions. And so the question is, can we, in the particular partitions, well, for the arc reversal walk, they're coming from partitions of the arcs of the graphs. And so the problem is to express this in more graph theoretical terms, and then so we get more information, get concrete information about the eigenvalues. Now to do that, we need some instance matrices. In fact, there are too many instance matrices going around now. So we're dealing with the K-regular graph on n vertices. And we have various instance matrices describing relations between vertices, edges, and arcs. Don't worry about the Oxford comment. So I'm writing down 4. The first one, dt, the rows are indexed by the vertices, the columns are indexed by the arcs, and there's a 1 if the arc starts on the vertex. So in that case, we say the vertex is the tail of the arc, and so this is the tail arc instance matrix. So there are n vertices. We've got a K-regular graph. There are nk arcs. Okay. Now the rows of this matrix would sum to the one vector because each arc starts on a unique vertex. Okay. Now, fairly obviously, once you've got that straight, then we get the vertex tail matrix. So rows indexed by vertices, columns indexed by arcs, but in this case, there's a 1 if the arc ends on your chosen vertex. So that's a second. Now, again, the rows sum to 1 because every arc starts or ends on some vertex. So these two guys, but if you transpose them, they become characteristic matrices of partitions. This would be the partition where you partition the arcs according to their initial vertex. This would be the partition according to the arcs corresponding to the final vertex. So I won't be going back to the partition language, but my point is these things fit naturally into that language. Okay. Now, I suspect you've never seen these before. This guy is what I would normally call the instance matrix of the graph. The rows are indexed by the vertices, the columns are indexed by the edges. If you look at the column corresponding to a given edge, there are 2 1s corresponding to the 2 vertices in it. Okay, and so that's going to be an n by n times k on 2 matrix. That's the usual vertex edge instance matrix that's discussed in many places. And finally, I've got a matrix M, which is arcs by edges. So there are nk arcs and nk on 2 edges. And as for each arc, you just write down the 2 edges. The edges, each arc, I've got this right way around. Well, you get a 1 if the arc is in the edge. That's probably the easy way of saying it. So we have these 4 instance matrices. Now, and it's these guys, well, they all matter, but so, yeah, so leave that. So DT is the transpose is the characteristic matrix of the partition of arcs by initial vertex. Okay, and so that's going to give us eventually give us the coin matrix for the arc reversal walk. And from M, we're going to get the R matrix. And the actual result is R is equal to MM transpose minus I. And C is the coin matrix, and it can be expressed in this form. And I'm not sure if the others are on the exercises yet or not, but they will be if they aren't already. So, so from these instance matrices, I can get R and C. Okay, and so in particular, in a sense, it's this and this. These are basically my projections. They're not probably scaled properly. So half of this is half of MMT is a projection. This should be 2 P minus I, and this should be 2 Q minus I. So there's some scaling missing, but so essentially this is my projection. So these are my 2 reflections. So what's happening is we're saying that for the arc reversal walk, well, we've got the 2 matrices in place of the, I was using L and M before. I apologize for that because this M is not the same as the previous M. I was running out of letters. So, well, and so this is saying more explicitly what I was just trying to say. I'm going to define some more matrices. No, it's 7. Or 9 if you count those 2. So I'm going to take K to be 102M, L to be 100D, DT transpose. Now that means that 2 KK starred, 2 KK starred minus identity is R. Okay, 2 L minus the L starred minus the identity is going to be C, and we're going to define S to be this. That's the bit. So it's vertices by edges. Now this is the matrix which is going to give us the eigenvalues and eigenvectors. Okay. So it's constructed from M and DT transpose. Maybe it'll help. Yeah, right. I want it. So the key thing, okay, so we decided that, well, the calculation we just did before tells us that it's the eigenvalues of this that matter. Now, the thing to notice is that from what we've done is that S transpose equals 1 and 2D times BB transpose, and BB transpose is the vertex instance matrix of the graph. Now, let's be a bit more concrete here. So B is looking like this. B transpose is looking like this. And so we're taking the dot product of pairs of rows of B. Now the rows of B are indexed by vertices, and the number of common ones is the number of edges that join both those 2 vertices. And that's either 0 if they're not adjacent or 1 if they are. So this is equal to A plus DI. Okay, so this is standard. And so we're getting SST given by this. Oops, I don't want to do that. And so we've finally come to the conclusion, okay, the eigenvalues of S transpose are going to be determined by A. And so this is going to be determined by eigenvalues of A. And so the eigenvalues and eigenvectors of the arc reversal walk are determined by the adjacency matrix, eigenvalues and eigenvectors of the underlying graph. Okay, which is why we're talking about it, because so at this point we see that the spectrum is determined by what I like to call combinatorial information, eigenvalues and eigenvectors of a graph. Okay, so again the details are in the references. Yeah, so I don't know if I need to add much to that. Now, yeah, one minor comment here is that our graph is deregular. This is falsely semi-definite, so the eigenvalues of this are non-negative. So that tells us we've got a deregular graph that tells you the least eigenvalue is greater than or equal to minus d, which we probably proved to some form or another earlier. The remark I want to make is that the least eigenvalue of a deregular graph is minus d, if only if the graph is bipartite. So in a certain sense, there's going to be two cases. So if this has eigenvalue 0, then this is bipartite. Okay, it doesn't cause a great problem. It's just that when you start going into the details of working things out, sometimes you've got to separate out two cases, and you'll see that in the next result, which I'm just citing. So if you've got a deregular graph, and U is giving you the arc reversal walk on X, then the multiplicities of the non-real eigenvalues sum to 2n minus 4 if X is bipartite, and to 2n minus 2 otherwise. Now, if lambda is an eigenvalue of X not plus or minus D, and we set cosine theta equal to, choose theta so the cosine theta is equal to lambda on D. Now, the eigenvalues of A plus DI divided by D lie in the interval 1 to minus 1. Okay, so this definition makes sense. And we have an eigenvector Y for lambda, then this guy is an eigenvector for U with eigenvalue E plus or minus theta, so plus E plus theta. So this is giving you an explicit formula for the eigenvectors in terms of the eigenvalues. And I chose not to drag you through that. What's the time? 2014. So so I showed you we have the machinery to get the eigenvalues and eigenvectors of the entry transition matrix for the arc reversal walk. More generally, this will work for bipartite walks. In particular, it'll work very nicely if you take a bipartite graph, which is semi-regular. The white vertices will have one balance, and the black vertices will have the other. So in that case, pretty much everything we've done carries through to that more general situation. So it generalizes. So this is not just a specific result, it's actually a toolkit. Okay, I'll say a bit more in a second. But so the point is we can get the eigenvalues and eigenvectors of the transition matrices for a wide variety of walks. I wanted the last 2 minutes to sort of change directions a little bit, though not much to change, it appears. So I start with the definition. So I'm going to start with this time with a directed graph, and the line digraph, LD of X, is the directed graph with the arcs of X as its vertices and an arc from AB to CD if only if B is equal to C. Now, we could allow X to have loops, but it simply changes nothing, so I'm not going to bother. Okay, so X is a directed graph with no loops. It could have multiple edges, multiple arcs. That's not a problem. Okay. The other thing is that we allow, if we haven't, we allow the line digraph. If AB is an arc, then as an arc of the line graph going from AB to BA. Now, in a sense, there are two schools of thought, whether you should allow this or not. Okay, I think this is what people usually mean when they talk about the line digraph. If we don't count this as an arc, then we get something which I will call a strict line digraph. So there are two flavors of line digraphs depending on whether you view AB to BA as an arc or not. And it really depends on your application. Okay, so, but I think I'm probably the only person on the planet that calls this a strict line digraph, so don't get too worried about remembering that term. Now, as for undirected graphs, we still have incident matrices DT and DH with the same definitions. And this is a straightforward exercise, and it is in the notes. We can express the adjacency matrix of the line digraph in terms of the head and tail instance matrices. And now, so this is DH transpose DT. So remember that DT is short and wide. So this is a big matrix indexed by arcs. If you look at the DH transpose DT, or the other, multiply in the other order, you get the adjacency matrix. Okay, and so X and the line digraph have the same non-zero eigenvalues, the same multiplicities. Now, one reason this is interesting is that the transition matrix for an arc reversal walk is a weighted adjacency matrix for the line digraph. Okay, so there's a standard structure under there. The weightings are coming because you're using the Grover coins, and these have, entries, diagonal entries aren't equal to 1. So that's where the weights are coming from. So now the other comment I'll make is that so in this case, there's no trouble getting notice that there's no particular problem getting the eigenvalues of the line digraph. You just read them off from the eigenvalues of the graph. The problem comes is because actually in our situation, we're fiddling with the identity. So we've changed the diagonal entries. And so we can't just appeal to this result. And so essentially, as the difference between the adjacency matrix line digraph and the adjacency matrix line digraph take away R, where R is the reflection, it's a permutation of order 2. Now, in general, if you take some matrix M and you subtract R, it's very difficult to say what the eigenvalues of the difference are. Okay, the machinery we've done earlier will actually let us do it in this case, but we won't worry about that right now. So my point simply is there is a connection between line digraphs and reversal walks. And it's in some ways line diagrams easy to work with. The other comment I wanted to make is a connection with classical walks. So we have what people call non-backtracking walks. So it's non-backtracking. If you go from A to B, you can't step back to A on the next step. So there's no subsequences ABA. So you're a non-backtracking walk, well, that's fine. And these arise in various situations. They're interesting objects in their own right. And so you can view a non-backtracking walk as a sequence of arcs. What's happening is, in a sense, you've got a random walk on a graph, but you've got to not only know where you are, you have to remember where you just came from. And so your state consists of 2 vectors, or 2 vertices, and the vector consists of an arc. So in some sense, the state at each stage is an arc, not just a vertex. And so a non-backtracking walk is a sequence of arcs such that A, B, and C, D are consecutive, and B is equal to C, and D is not equal to A. Okay. Hence, a non-backtracking walk can be viewed as a walk on the strict line digraph. Okay. And so again, there's a connection to non-backtracking walks. There are 1 or 2 papers about non-backtracking walks and discrete quantum walks, but I don't understand anything very well there at this point. But it's an interesting connection. Non-backtracking walks are also related to what they call Ihara zeta functions on graphs, so that there's a bit of fun to be had there. And that's where I'll stop.